All right, guys, welcome. Let's get started. As a reminder, we're going to meet on Tuesday over at the Army Corps of Engineers office. That's on 5th Avenue, and we need to be in the lobby at 9 a.m. And you may need to bring ID. I think they have some security requirements. Everyone has to be a U.S. citizen, which I don't think is an issue, but please be sure to bring identification with you. We're going to get to see a little bit more about the modeling that they do and I think the monitoring of the assets that they own. So also the homework assignment that I gave you last time, that's due on Tuesday. And on Thursday of next week, we're going to start going over WMS. So please download and install that. Has anybody already done that? Any problems with the license code that I gave you? It all work fine? Good. Very good. All right. Well, today what we're going to do is I'm going to tell you a little bit about a project that I did while I was on sabbatical leave from Marshall. And I don't think I've showed you guys this presentation before. Did I last year in fluid mechanics tell you about this at all? Yeah. All right, well, we're going to go through the whole presentation because it relates into some ideas that I'm having for anyone who's interested in doing hydraulics and hydrology for senior design. I've been thinking about that, and I think I'd only be able to accommodate one group of 3 to 4 students maximum. So telling you about this project that I did in the UAE may familiarize you with some of the methods and equipment that I have in mind for the senior design project. So I thought that would be relevant based on the timing. So this is a presentation that I gave at a conference last February. I guess it's this past February. And it was to basically just report on some of the stuff that I did when I was on sabbatical over in the UAE. And it was in collaboration with a colleague that I've got over at the American University of Sharjah. Sharjah, by the way, is one of the 7 emirates of the United Arab Emirates, and it's right next to Dubai. People over there aren't always familiar with where West Virginia is. People sometimes have heard about Virginia, but I have to always point out whenever I'm outside the United States, where is West Virginia, and talk a little bit about its unique topography. A statistic that most of us don't realize is that in West Virginia there's more than 200,000 bridges and culverts, and so there's really a huge number of hydraulic structures, and that's just in the Division of Highways inventory. So that if you include locally owned and privately owned bridges and culverts, it's probably at least double that. So there's a lot of situations where we need to know what is the flow rate for some stream in order to correctly size a bridge or a culvert. And so the outlet that I'm speaking about when I do watershed modeling is just some location where we're going to have a road crossing a stream. And an outlet doesn't necessarily mean that that's the last place the water is going to go before it goes into a larger water body, but anything upstream of that watershed outlet of interest is the basin that we have to delineate and put together a model for. And so the driving question is, how big should the culvert be? And the culvert sizing is partly determined by the materials that we'll use and the slope of the channel at a certain location, but it's more largely influenced by the characteristics of the watershed. And so the size depends on the flow rate that we have to estimate with the model. And the sad thing is that in West Virginia there are only about 100 stream gauges across the state where the USGS is measuring flow. So there's not a lot of places where we actually have historical data. And I had a project a couple of years ago where I was working for the Division of Highways, and we picked 15 very significant bridges in their inventory, and of those 15 there was only one that had a stream gauge anywhere nearby, and all the rest of those 15 had been sized just based on estimation and extrapolation and projection. So you can see how spread out those stream gauges are, and here we are in Cabell County, and although there are some stream gauges on the Ohio River, none on the interior watersheds inside of Cabell County. And so we can't always rely on active measurement to give us an idea of what the flow rate through a stream might be. And so we have to have a prediction approach. And the thing that makes predicting tricky in West Virginia is the models that have been developed in other locations aren't broadly applicable to the conditions within West Virginia. So you all have already been exposed to the NRCS approach, where it says that we can look at the land use and the soil type characteristics inside of a watershed, and based on those identify a composite curve number for the watershed, and then knowing the curve number informs how much storage there would be, and then when you know a precipitation amount, you can calculate the runoff, or in other words, the rainfall excess. So this is a pretty good approach for estimating the depth of runoff that there's going to be, but it doesn't specify the timing. And so you'll remember that the NRCS method is a two-step process, one defining the runoff depth, and then the other is assigning that runoff depth to some sort of a temporal distribution. And so the second part of the NRCS method was to use a runoff hydrograph. And the key to knowing the timing of it is to estimate the amount of time between when the rainfall event is and when is the peak. And so that lag. The lag time, everything else is tied to that. And so of course there are methods that can be used to estimate the lag time, but that's just an estimation. And this equation is an empirical equation that was generated based on a series of measurements that were out in the environment, and actually those measurements weren't in conditions that are similar to West Virginia. You know, West Virginia has uniquely steep watersheds, and so the question is, how can we extrapolate an equation like this into conditions that are far steeper than it was originally generated with? The variable y is the watershed slope. And so if I'm remembering correctly, this SCS method for estimating the lag time had watersheds about 10% and less as the average watershed slope. Whereas we can routinely in West Virginia have watershed slopes that are in the 40 to 50% range. And so that's just off the charts extreme in terms of the slope. And so estimating the lag time is the big unknown in trying to figure out how much flow rate is going to be at a culvert at a given time. Because the depth, you know, the absolute runoff depth is easy to estimate, but the timing of when it arrives is really what determines how big the culvert's going to be, not the runoff volume. It's the peak runoff flow rate that governs. So you already know stream response means the runoff hydrograph relative to a rainfall hyetograph. And so conceptually speaking, a flashy watershed is one where there's an immediate response to a pulse of rainfall. So you have a pulse of rainfall, and a period of time later there's a distinct peak in the runoff. And those are characteristic of small watersheds, and particularly small watersheds that are steep. But a large watershed is going to have a more muted response to where the runoff peaks kind of blend together. And you can't discern the individual effect of different segments of the rainfall hyetograph in a large watershed. Cody, are you working on a paper or something? What you working on? All right, so what we need to do is understand the time delay from a rainfall pulse to the peak of the hydrograph. And so what I wanted to do was actually physically measure that. Take instruments into the field and figure out if that equation, if the SCS equation for measuring lag time is realistic. So I wanted to do it for small watersheds because those are the ones that are most likely to not have actually measured data for. And small watersheds are important because those are the ones that most often we're going to have to put in a culvert for. If it's a large watershed, then there's going to be a bridge and a more sophisticated hydraulic and hydrologic analysis can be done. But it's the small watersheds that we really have the low-hanging fruit for improving the way things are done. I was interested in steep watersheds because those are the conditions across the state here, and extreme land cover characteristics. And let me tell you a little bit more about what I mean by extreme land cover characteristics. You know, in West Virginia, we are at one end of the spectrum in terms of undeveloped. And that's actually one of the things I like most about this state, is the fact that there isn't a strip mall on every corner, and that they haven't paved over every square inch of the state, that actually there are places you can go that are still wild and heavily vegetated. And so here's a picture of a bunch of ferns inside of a forest, and you would just imagine that there's going to be quite a lot of abstraction that has to be satisfied here before there's any movement of the flow over the surface. You just think about all of these ferns having to be wetted, and that the runoff peak is going to be much lower than it would in a paved watershed, or if maybe if a mountainside had been stripped for mining purposes. Well, so this is one end of the extreme, is heavy vegetation. Another end of the extreme, besides urbanization, is a scenario where it's still undeveloped, but where it's very arid, and that there's no vegetation or forest litter to slow down the movement of water through the watershed. And so this is a picture that I took when I was in the United Arab Emirates, and it's in a location called Wadi Shauka. And Wadi is similar to a holler. It's just the colloquial term for like a small watershed or a depression. And so when it rains here, it's steep like it is here in West Virginia in this watershed, and they have small catchments in the same way that we have many small catchments of interest, but the difference is that the vegetation is very sparse, and it's not likely to have as much of an initial abstraction effect. So part of the reason why estimating the lag time is so important is because water can cause a lot of damage. And this is a picture of conditions in Richwood, West Virginia, after the flood that they had. Now, I think it's been almost 2 years ago. So there's plenty of places across the state that have received economic damage and loss of life because of the excessive flooding. And if we had a better way of predicting what the peak flow is going to be, then the hydraulic structures could convey flows more effectively. Here's a picture of flooding in the Middle East. And so it's not just in wet environments like we have, but also in an arid environment it's a problem as well, because people don't think of the need to convey stormwater when it only rains a couple of times per year. But it can be a real issue. This is a highway underpass that was completely flooded because of lack of drainage. Here are some neighborhoods that were, these are nice houses, and the first floor is underwater because of heavy storms and a lack of drainage network. So the question is what to do with the excess water. In a lot of cases it's just conveyed right out to the ocean and not made a use of in an effective way, but when you have a better understanding of the timing and the amount of water, you can do things instead like building dams and try and improve the recharge of groundwater. And that's what this Wadi Medina Dam is. This is in the same region as that Wadi Shauka picture that I showed you before. This is a dam where there's a little bit of agriculture in the area, but the main purpose of this is to promote infiltration, and so that less of the water rushes into the sea or evaporates senselessly, but trying to get more of it down to recharge aquifers that over the last several decades have been depleted pretty severely in the UAE. Most of the time the dam and the reservoir is empty, but you can tell that this has had water in it relatively recently. It's still, the soil's a bit moist. Here's a picture of the dam when it's got water in it. And so, I took this picture. There are plenty of times during the year where it's doing its job and infiltrating the water. And it's actually pretty scenic out there. It's a pleasant place to visit. I happened to be out there gathering some data one afternoon when a farmer kind of gestured at me, "Hey, come check out my farm." And so he gave us a tour of the onions and lettuce, and this is just a desert area where it was, you saw the pictures before, it's really desolate. But with a little bit of careful management of the naturally occurring groundwater, then they can amend the soil with a little bit of organics, and then there's enough rainwater through the year that the crops can kind of erase some of the need for importing food all the time, which is what the UAE generally does, is imports their food. So this kind of illustrates that water can be thought of as a risk, but also as a resource that needs to be preserved, and some of the opportunities it presents when we treat it like a resource. So this is a watershed that I was actually instrumenting, and this is a Google Earth look that just kind of exaggerates the vertical elevation differences within the watershed. Here's the actual photo of that same location. So it was relatively steep, and I picked this location because it matched some of the characteristics of a similarly sized and similarly sloped watershed that I'd instrumented in the United States prior to this time. And one of the things I wanted to study was the effect of slope on the time of concentration in such an arid watershed. And I also wanted to look at the effect of land cover, because I was doing a compare and contrast between a watershed in West Virginia that was heavily vegetated and a watershed in the UAE that was almost entirely unvegetated. These are the instruments that I was using. On the left here is a stream gauge sensor, where what it usually does is measures pressure and temperature, and it can go underwater, and you can program how often you want it to be measuring pressure and temperature. And what I would generally do is have it measure those in 1-minute increments, so that when it starts to rain and the stream levels increase, it can sense the increased pressure due to water above it. It records that, and then you can sort of back calculate how much of the pressure is the atmospheric component and how much of it is actual increased depth. So you'd have one of these pressure gauges just out in a dry spot to kind of subtract out the baseline atmospheric pressure, and then from the increased pressure you can estimate the depth of flow. The other instrument that I was using is a rain gauge, and this is a tipping bucket rain gauge that has an onboard sensor that anytime 1/100th of an inch of rainfall gets into this, it tips a little, it's kind of like a seesaw type thing, and it records that tip, it records the time of it, and so that you can get the intensity of the rainfall at any given time during a storm. So I put this stream flow sensor in a big metal pipe that had holes drilled in it, hoping that all of these rocks wouldn't bury the sensor or damage it, and set it all up and hoped that it would rain. This gives you a look inside that rain gauge sensor. You can see there are 2 sides to the tipping bucket, and so it fills up enough water and it dumps one side out and exposes the other to this cone-shaped kind of like accumulator, where all of the rainfall for the circular area exits out through that discharge point there. So it looks pretty bleak. Here's my rain gauge set up. There are some clouds out in the distance there, but there are years where it doesn't rain at all. And so I was over in the UAE for a year, and I was just hoping to be able to do this research, but it all depended on something I had no control over. I can't make it rain. And so I kind of had my fingers crossed. Within the UAE, I had 2 different watersheds that I was studying. One was pretty small with an area of 1.2 hectares, the other 7.8 hectares. They were fairly steep slopes within the range of what we might see here in this area. And when I put it through the NRCS method for measuring the lag time, this is what it would estimate. 12 minutes for the small watershed, about 30 minutes for the large watershed. Based on, remember, what goes into that is the curve number and the slope of the watershed. So I set it all up. I had to come back out every month to get the data off of it, but did it rain was the big question. And fortunately, conditions were right for a heavy winter. There were articles in the newspaper that were predicting, because of El Nino, that it was going to be especially wet that winter, and it was. There were several storms that I was able to measure with the tipping bucket. This is showing the rainfall intensity, centimeters per hour. And so there was a nice storm on January 3rd, one on the 17th of February, another storm in March, and another one the day after. The 17th and the 18th of February had some good storms with heavy intensity. So I was gratified to see that there was a measurement of rainfall, but you can have rainfall but no runoff, remember, because you have to satisfy the initial abstraction before there's any flow. So not only did I have to have rainfall, but there had to be enough so that all of the surfaces were wetted, and then flow would start moving through that dry stream bed that normally has nothing in it. So was there runoff? There was runoff. Now I'll spend a little bit more time on these figures to illustrate what it's showing. In red is the rainfall intensity, and so if you look over here on the left axis, that's the precipitation intensity scale. And then over here on the right axis is the stream depth in centimeters. And so what's illustrated here are the small watershed in blue and the large watershed in green. And this line is indicating the distance between the center line of the rainfall event to where I observed the peak runoff that's resulting from that rainfall event. And so it's a little bit of an art trying to figure out, where is the peak that you want to say is, our main high point of runoff. But after looking at several of these hydrographs, I got to the point where, I try to distinguish between this pulse and then follow-up rainfall, looking for inflection points in the graphs. Sometimes it was easier than others to identify those obvious inflection points and what the time of concentration was. So here's the experimental data compared to the prediction that comes out of the NRCS equation. So for the large watershed, remember that had a predicted lag time of 29 minutes. But the measured lag time for the large watershed was only 9 minutes. And that's because it was so steep, there was no vegetative cover, and so the water was moving very easily and very quickly through that arid watershed. And through the small watershed, it was even quicker, simply because there's less distance that the water has to go over the land before it gets into the channel and towards the sensors. So I was predicting 12 minutes, and it was only 4. So there's roughly a factor of 3. It's pretty consistent that the predicted lag time was 3 times longer than about what was experimentally measured, and for the small watershed it was about 3 times longer than it actually was observed as well. So that was I thought a relevant finding, that the peak flows are arriving much more quickly than the SES method would predict, and it's because the SES method is underestimating the effect of how steep that slope is. The lag time varied as a function of rainfall intensity. If we go back to this data, you'll notice that sometimes the lag time was 15 minutes for a small storm, but only 5 or 6 minutes for the larger storms. And so if you look at these rainfall intensity, when the rainfall intensity is low, then the lag time is longer. When the rainfall intensity is high is when the lag time was observed to be the least. And so it's a rational, understandable effect there, that when you're wetting the surface more quickly and overcoming the initial abstraction in a very short time period, then the lag time is going to be less as well. Comparing these results in the UAE to data that I already had in West Virginia, it kind of allows for you to specifically tie differences in lag time to the land cover, because the slopes were the same, roughly. And when I did that, when I compared to the bare land use, lag time is doubled in West Virginia. And so the SES method still overestimates the lag time, but not by as much as it does in the UAE. Remember I said that in the UAE it's about 1/3 of the actual lag time is about 1/3 of that which is estimated. But when you have vegetative cover like we have here in the state, it doubles the lag time compared to just the bare earth that's steep. So I mean, some of the implications of that can be extrapolated to mining, like the coal mining that they do, where they say they're going to reclaim the land after extracting the resources, but they really just kind of sprinkle some grass seeds on a dead hillside and say, oh, we've planted, it'll all grow back and be vegetated again. It kind of doesn't really work out very well. So we can expect that the lag times are going to be accelerated when there are things that have been done to clear the hillside. So I have a colleague who's still over there gathering data on additional watersheds, because just having this done in 2 watersheds is good, but if you really want to have some statistical robustness and be able to say that this is a trend that isn't attributable to random chance, you have to do it in a few more. So the applications, of course, have to do with the sizing of culverts. These culverts are really large. To give you an idea of the scale of them, they're about 12 to 15 feet tall, these culverts in the UAE. Because the lag time is so fast, I think that the data also suggests the relevance of having more of those groundwater infiltration dams that I showed you some pictures of. If you have them relatively smaller and more frequent dams like that, then there'd be less sediment being transported. They have a problem at their existing groundwater recharge dams of really fine sediments kind of plugging the soil and decreasing the amount of infiltration that there can be. But if there were dams more often, then that would reduce the velocity of the water, and it would cause less scour of the sediments, and so that the recharge wouldn't be as limited on the surface there. So you can see that there are some cracks in it, in the earth here, but there are a lot of fines that end up at the surface, and the soil conditions limit infiltration as a result. Okay, so that's an idea of what I did over in the UAE, and in particular I wanted to tell you a little bit about this equipment, because the idea that I have for if there's a group that wants to do a hydraulics project for the senior design, I have in mind that they'll be using the same equipment, the rain gauge and the stream gauge, in order to try and calibrate a watershed model. All right, I should have animated this. This is a lot all at once. Let's see, can I do that? Seems like it's going to be such a huge project, right? Oh, that's just going to be all at once. Anyways. Okay, so all right. You're going to learn how to use WMS starting next week. And so if there's a group of students who want to do a senior design project in hydrology, then what I'm going to do is I'm going to identify a watershed, and I'm going to say, let's size a culvert for this watershed, and go all the way to a calibrated model for that. And so the first thing you have to do in developing a watershed model is getting the land use, the soil type, elevation data, and so on. And so you'll learn how to do that very easily. It's easy to throw together a watershed model, but calibrating it is really the tricky thing. And so gathering rainfall data and stream flow data is going to be part of that. So the student group is going to have to go into the field every couple of weeks and download the data off of the sensors, because you never know when it's going to rain, and the sensors can only have about 30 days of data on them before the memory fills up, depending on how frequently you've got the sampling set at. If it's 1-minute intervals, then you get 30 days. If you do 30-second intervals, then it's 2 weeks. So the group will get the rainfall and the stream flow data to try and get the relationship not only on the amount, you know, when you have an inch of rainfall, you saw what increased depth, but also the timing as well, because we want to calibrate the runoff volume and also the runoff timing, so the lag time, similar to what I was just describing. So you'll be able to calibrate the watershed model. The student group will also have to do some surveying to go define the channel, because the hydrologic model will just tell you the flow rate Q, but it won't tell you how deep the water is going to be unless you put that into HEC-RAS or some other model that relates flow rate to depth. And so there is like elevation data at a pretty coarse resolution, but for a small watershed you need a pretty precise idea of what the channel cross-section looks like. And so, you know, the student group will go and do a survey to try and find out at certain points what does the channel look like, so that when you have a flow rate you'll be able to know the relationship between Q and the depth. And so you're going to have to teach yourself how to learn HEC-RAS if you don't already. I think maybe a couple of you have been exposed to HEC-RAS maybe in internships or something like that, but that's something that I've had student groups do before in senior design. In fact, one of them made a video that's posted on my YouTube channel, kind of like a brief 1-hour tutorial of how to very quickly get acquainted with HEC-RAS and find out flow depths when you know the flow rate. So then you'll use HEC-RAS to model the stream, tying it together with the hydrologic model. So we want to know for a certain rainfall what's the runoff, and then what is the depth, because in the end you're going to be designing culvert alternatives, you know, looking at concrete box culvert, looking at corrugated metal, putting together some cost estimates of different alternatives, and then, you know, selecting the most economical of those alternatives to be hypothetically built in the location. But so since it came up in the last class, the idea of I think you're having to start to nail down what projects you do for senior design, I wanted to introduce this idea to you. So now that you see how much work it's actually going to be, maybe some of you are less interested than you were before, but I just want to get a quick idea. How many of you are still interested in hydraulics, hydrology? All right. So I see 5 hands, and I said this is a 3 to 4 person job. So I'll have to talk to Dr. Michelson about what approach he wants to do in eliminating, like if it's going to be an octagon or just a normal like boxing match, you know, how you're going to decide. But that's the idea that I've got. I still need to figure out the location, but that is something I could do relatively quickly. And so we need to get those sensors in the field as soon as possible, because you know, we're getting into the wet season now, and what you really want to do is, you know, size your culvert for a 5-year storm or a 10-year storm. There's probably a pretty slim chance that we're going to see a 5 or a 10-year storm in the next few months that you'll be working on senior design. But there's still value in calibrating a watershed model for smaller storms. You know, if it's calibrated for an 0.8 of an inch storm, that's better than not being calibrated at all. So. All right, so that's all I have as this recorded lecture part. We're going to watch the rest of An Inconvenient Truth now.